Hello and welcome back to Trig Review. So today on the menu, special from the chef, right, is Trig Identities and Trig Equations. Now we are going to take a look at the ways that trig functions work with each other, and then I will solve some equations in preparation for the almighty calculus. So we start by first listing all 6 trig functions we have: sine x, cosine x, tangent x, those are the main 3, and then we also have cosecant x, secant x, and cotangent x. So there they are. Maybe I can put them in a purple box and separate them with lines. So these are the creatures that we are going to use, and they work together. We start with some of the basic trig identities that you must know, and that's tangent x is equal to sine x over cosine x. We talked about this one earlier. And then you have the cotangent x, which is cosine x divided by sine x. These guys have vertical asymptotes whenever the denominator is equal to 0. So cosine x is equal to 0 at every pi over 2 and 3 pi over 2 and 5 pi over 2 and so on. So anything pi over 2 is going to be the cosine equals 0, so vertical asymptote for tangent. And then pretty much the same for cotangent, every pi. So 0, pi, 2 pi, 3 pi are all zeros for sine. And then we have the reciprocal identities. Let's put these, let's say, green, whatever. Cosecant x is 1 over sine x. Secant x is 1 over cosine x. And then cotangent x is 1 over tangent x. Now this one, last one, ties in very well with these two guys here. You can see the sine over cosine, cosine over sine, because it's 1 over tangent. So they all work together. These are the most basic identities that are there that connect these functions. But then there are a lot of other cool stuff that we can come up with. So these are some of the basics. And now we look at Pythagorean identities. So for Pythagorean identities, there are 9, right? But technically we only look at, we can memorize 1 and then get all others when we employ the stuff from above. So the main one is sine squared x plus cosine squared x is equal to 1. So this is the boss equation, all right, for Pythagorean identities. And there are many ways to show this. If you observe in the unit circle, say you have this triangle here, you know that these coordinates here are cosine x comma sine x. So when you drop down this vertical to create 90 degrees for the right triangle that you see, since these coordinates are cosine x sine x, and you know this hypotenuse is 1 because it's a unit circle, you have this one over here and this one over here. So the one on the bottom is cosine x and the one on the side is sine x. If you have a squared plus b squared equals c squared, you can definitely see that it's sine squared plus cosine squared equals to 1 just by looking at that So you can see from the relationship from the basic unit circle that what we have as a Pythagorean identity is true. Now I promised 9 identities, and this is only 1. Well, the other 3 are actually just manipulations of this one. So there are 2 more that are with sine and cosine, and that is just shoveling terms around. So I guess less important here. You can say that the sine squared x is 1 minus cosine squared x, and cosine squared x is equal to 1 minus sine squared x. So these are also Pythagorean identities, right, using the sine and cosine. All right, 6 to go. Now going back to the original one, if I am to write sine squared x plus cosine squared x equals 1, and if I am to divide everywhere by cosine squared x, so what I did is I divided everywhere by cosine squared x, you get another very important identity which says that tangent squared x plus 1 is equal to secant squared x. And this one is again one of the main ones, and then we can flip it to get that the tangent squared x is equal to secant squared x minus 1, and we can also say that 1 is equal to secant squared x minus tangent squared x. So those are again lesser, should I say less important. So the main trig identity is the one on top, sine squared x plus cosine squared x equals to 1, and then by simply rearranging terms we get the other 2 in blue. Then we go and reset, go back to the original equation, divide everywhere by cosine squared x, and we get the one with the tangent secant as a pair. And now we again go back to original equation, write sine squared x plus cosine squared x equals 1 once again, but this time around we divide by sine squared everywhere. And what we have is another one of the big formulas, 1 plus cotangent squared x is equal to cosecant squared x. So this is another major one. And then rearranging terms, we get the other 2. So cotangent squared x is equal to cosecant squared x minus 1, and 1 is equal to cosecant squared x minus cotangent squared x. So there are 9, as you can see, 9 formulas with these flavors. There are 3 main and 6 that we get just by rearranging terms, and they all pop up here and there, especially in Calc 2. So they are necessary. Now, as I said, you have to know the first one on top, and then the ones that I boxed in red also show up frequently. The other ones is just, being a little bit smart to manipulate these terms the right way. So those are the trig identities. And it's very important to see that you have this 1 equals to. In each one you have the 1 equals to the stuff. It is useful in certain applications and certain problems. It is useful to know that you get to write 1 equals, and then one of these forms will actually help you solve the problem. So it's an interesting way to write 1. Or to annoy people. What's the time? You just say cosecant squared minus cotangent squared, and you walk away because it's 1 p.m. And then let them figure it out. I know. I had a friend wrote a check using these things once. I have a picture of it, actually, if anyone is interested. Anyway, so these are the basic trig identities. We have 6 trigonometric functions, and then the 6 trigonometric functions, we have the basic functions, basic identities that are through division related, that through division relate the most basic fundamental functions. And then we immediately move into Pythagorean identities, where you have 3 main ones, and then the rest is all manipulating the terms. So we actually have 9. There is something about like 7,000 formulas in PreCalculus 2 for trig, but it's very rich in terms of these identities and stuff. But you know, if you know your way around, you can quickly come up with these things. The next set of extremely important identities are the sum and the difference of these, and then the double angle, half angle, and then power reducing. The sum to product, product to sum generally don't show up until differential equations, I would say. And generally we give formulas just for those 8, sum to product and product to sum, but the rest you should know, especially if you're going to Calc 2. So let's start with sum and difference formulas. So we have sine of x plus y. So this would be the saying that you want to calculate sine of, let's say, 75 degrees. 75 degrees doesn't fall on 30, 45, 60, right? So can you calculate that without the calculator? And the answer is yes, because 75 degrees you can write as 30 plus 45. And then you can use this formula to expand and calculate. So let's say you have this, so that's going to be sine x cosine y plus cosine x sine y. You just swap them. And if there is a minus in parentheses here, there will be a minus on the other side. So red plus with red plus and blue minus with blue minus. You can also have, let's say, sine of 15 degrees, which would be 45 minus 30. So you can solve all of those problems. Now, again, this is one of the major formulas. I'm going to write later cosine and tangent, but let's just quickly take a look at sine of 75 degrees is sine of 30 degrees plus 45 degrees. And we know how to find sines and cosines of 30 and 45 degrees, so we can use this formula to separate everything. So we have sine of 30 degrees, cosine of 45 degrees, and then since this was a plus here, we will put plus there. Cosine will be swapping them, so sine keeps the sign. And then we have cosine of 30 degrees, sine of 45 degrees. And now sine of 30 is a 1/2, cosine of 45 is root 2 over 2, plus cosine of 30 degrees is root 3 over 2, and sine of 45 degrees is again root 2 over 2. So when you combine all of this, you see it's root 2 plus root 6 divided by 4. And this is the exact value. So sine of 75 degrees is exactly root 2 plus root 6 over 4. And we were able to calculate that because of our formula up there. It's just, you know, plug and pray, I guess, that there will be no issues in calculation. How much is sine of 15 degrees? Sine of 15 degrees would be sine of 45 degrees minus 30 degrees. And then you will use the same thing. So you have sine of 45 cosine of 30 minus, because it was minus there, cosine 30 times sine 45. So we can compute all these things. So it's a root 2 over 2. Cosine of 30 is root 3 over 2. Minus cosine of 30 is 1/2. And sine 45 is root 2 over 2. And now we get root 6 minus root 2 over 4. So this is why, I mean, we use this in proofs and later on integrals and everything else. But we can also compute little angles. Clearly, you can't use this to compute, let's say, sine of 19 degrees, because you can't make 19 in terms of 30, 45, right? But the question can ask you to compute, you know, 115, you know, or anything that you can put together with these 30s and 45s and 60s, right? So 60, let's say, plus 45, that's 105. So 105 is okay. You can figure out 105, sine of 105 by simply writing sine of 60 plus 45, and then there you go, it's 105, and then you go from there. So as long as you can express the angle that you are given in terms of some of the known angles, which is 30, 45, 60 and 90, you don't need 90 because that you can just use reference angle. As long as you can express a combination of 30, 45, and 60, you can calculate using these formulas. Now, these formulas are actually used to give us something much more important later, as I said, but you can do these cute things as well. Now, the cosine one of x plus y is going to be cosine of both. So cosine x, cosine y, and now it's a minus sine x, sine y. And if you have a minus in the parenthesis, you have a plus in the formula. So they flip. And I will box this one. Again, also extremely important formula. And then the use of this is going to be exactly the same as the one for sine. You are going to use the 60 minus 45 to get 15, or 45 minus 30 to get 15. So whatever you come up with. And the last one that we cover, these ones are rarely used, but they are around, is the tangent of x plus y, right? Which would be the tangent of x plus tangent of y divided by 1 minus tangent x tangent y. And I'm going to put this one in the red box. It's important formula, but it's again not as crazy. And if you change the sign, you have to swap the other signs on the other side. So there are two formulas in each one of these boxes, one for plus, one for minus. You follow the red signs for pluses and blue signs for minuses across the formulas. So now I would like to solve some trig identities. So let's take a look at a few examples before we push with another set of 10 formulas. By the way, how many formulas do we have so far? It's probably a million, right? You just had 6 over here if you separate pluses and minuses. Then we had 9 for Pythagorean, so that's 15. And then we had the 2 basic tangent and then another 5. So we had 20 formulas so far, if you put them all on the pile and count each one separately. How many formulas do you actually have to know so far? 5. So you see, it's the rest are all derived from it, and it's going to be even more. The cosine formula will give us insane amount of good formulas coming up next. But let's first think about some of the identities. I just want to find some problems here. There we go. So this is a very interesting. So verify identity, and they give us in a problem 35 cosine of x minus pi over 2 is equal to sine x. Now, depends on how much practice you did over the weekend. You might see, right, whether this is right or wrong by simply examining graphs. So identity could be whatever we write, could be right or could be wrong. And we can use these formulas we covered so far to prove that. But you can also say, oh, wait, what was my cosine graph? My cosine graph looks like this, and now I'm supposed to move it to the right, pi over 2. So it's going to look this way. Oh, wait, that is a sine graph. So, yeah, this sounds good. It sounds good. But let's try and solve this using our identities. So now, we are going to use the cosine formula, this one. So the cosine would say, so the left-hand side is cosine of both. So cosine of x, cosine of pi over 2, and then we change this sign, and then sine of both, which is sine x and sine pi over 2, and then that should be equal to sine x. All right. Well, cosine of pi over 2 is 0. So the entire first term dies. And the sine of pi over 2 is 1. So what you have is sine x times 1 is equal to sine x, which is true. So these are like little proofs that you can do. You show that sine x is equal to sine x, which means that the identity that was given to you is correct. I could have write anything. I could say cosine of x minus pi over 2 is equal to tangent squared. And of course it will not work because the left-hand side computed to be sine x. So we can write anything down, but some of those will be true and some will not. That depends on what we use as formulas. Let's take a look at another identity, something similar. It says cosine of alpha plus beta instead of x and a y plus cosine of alpha minus beta is equal to 2 cosine alpha cosine beta. Now you can't really check this one with graphing, right? Again, verified. you could use alpha equals 60, beta equals 30, and then, compute to try and see if that's going to work out. But again, you just worked out one example out of infinitely many that you can. So we worked this out using the formulas. So now we expand left-hand side and leave the right-hand side as is and make sure that the left-hand side actually simplifies and computes into what we have on the right. So cosine alpha plus beta is cosine of both, so cosine alpha cosine beta, minus sine alpha sine beta. So this is the left-hand side expanded. And then we have this plus sign, and I generally like to point out arrow to it so it's clear which sign is that one. And then we have cosine alpha minus beta, where we write again cosine of both, so cosine alpha cosine beta. And then we change the sign from minus to a plus, and we have sine alpha sine beta. Please observe that the blue terms are identical and have opposite sign, therefore they cancel. And the underlined terms are the same with the positive sign, so that's like apple plus apple is 2 apples. So 2 cosine alpha cosine beta is equal to 2 cosine alpha cosine beta, and the identity is verified because we have left side equal the right side. It's computation. It's computation. You grind through these, and there you have it. And just in case these problems look too good to be skipped, 57 to 64, these are computation problems. So you are supposed to figure out the value of sine alpha plus beta. Compute sine alpha plus beta given, and now let's say 58. This is what they give you. Sine alpha is 4/5 in quadrant 1, and sine beta is 7/25 in quadrant 2. This is all they give you. And you are supposed to figure out the rest. They can ask for sine alpha beta, they can ask for tangent alpha minus beta, they can ask for anything. It's fine. Now, when you write the formula, so solution. When you write the formula for sine alpha plus beta, you quickly find you have sine alpha cosine beta plus cosine alpha sine beta. And now if you look what you have this one, you don't have that one, you don't have that one, but you have this one. So you have to figure out the values for those so you can plug them in. See, the sine alpha will be replaced by 4/5. So sine alpha is 4/5. And sine beta is 7/25. So those values you can swap immediately. The problem is that you don't have the other two so that you can compute all 4 of them. So now what is the cosine of beta? Well, You have sine alpha is 4/5, and you have the quadrant 1. This, in the unit circle, gives you a quadrant 1 triangle where it's not a unit circle anymore because it's actually now the radius is 5. But you know that sine is opposite over hypotenuse, so you have a 4 and a 5 on a hypotenuse. So how much is the missing side? Right? And the missing side here, using Pythagorean identity, is the square root of 25 minus 16. 25 minus 16 is 9, and square root of 9 is 3. So that implies, all of this implies that the cosine alpha is equal to 3/5. And it's in quadrant 1, so it's positive. So this calculation was done to figure out the missing piece of cosine alpha. I found cosine alpha. So I start with sine alpha. I draw the, can't call it unit circle because it's not unit anymore, it's 5. So circle with radius 5. You have the hypotenuse because sine is opposite over hypotenuse. The height is 4, that's opposite. The 5 is on the hypotenuse, and then we use Pythagorean theorem to figure out the other leg. We came up with 3. So now we have the triangle 3, 4, 5, famous Pythagorean triplet triangle, and the cosine is adjacent over hypotenuse, so the one that we just calculated is 3, so 3/4. I could have asked the tangent question over here. You will be able to find tangent because tangent will be 4/3, right? You can find anything now because you have all 3 sides of a triangle. So we figure out cosine alpha, then we plug in here. So that's great. We have sine alpha given. Now we calculate cosine alpha. We have sine beta given. Now we need to use the same method to figure out cosine beta. So it's the same principle. Draw the triangle. This time hypotenuse is 25. So now we're using the fact that sine beta is equal to 7/25, and it's in the quadrant 2. So we draw the circle, and it's a quadrant 2 now, and I have a 25 here, and this line over here is 7. So the one that we are looking for, one on the bottom, is going to be the square root of 25 squared minus 7 squared, right? Now that's, I believe, 625 minus 49 as a square root. So we have a square root of 625 minus 49, and that works out to be 24. So now all of this information here tells us that the cosine beta is adjacent over hypotenuse, which is 24/25, cosine beta equals negative 24/25. Why negative? All students take calculus, cosine is negative. Here, I'll write it in blood. Cosine is negative in quadrant 2. This is what we did on Friday. All students take calculus, the quadrants in which these guys are positive, negative, and so on. So All are positive. Sine is only positive. That means cosine will be negative. And we are calculating cosine beta in the second quadrant. Since cosine is negative, you have to put negative 24 over 25. Yay! I have everything now. We can go and compute our sine alpha plus beta. So sine alpha was 4/5 times cosine beta, which is negative 24 over 25, plus cosine alpha, which we calculated cosine alpha is 3/5, times sine beta, which was 7 over 25. And there you go. So 4 times 20, that's a negative 96 plus 21 divided by 125, 25 times 5. And when you subtract 21, you get 70. Is there a 75 there? Negative 75 over 125. We can cancel by 25, get negative 3/5 as the answer. It's a beautiful problem. It's convoluted, but yeah. You know what it's good for? When someone tells you, what do you know? You write this up. You know that people stop annoying you with that stupid phrase? What do you, especially if they say, what do you know, I have kids. Really, that's the real level of, you know, there's a PhD in having kids, and now, you know. I said, okay, let's take a look at this. So, that's the measure of. So there you go. The question clearly says compute sine alpha plus beta given sine alpha and sine beta. You found cosine alpha and cosine beta because you need them for the formula, and you just plug everything in, sine alpha for sine alpha, cosine beta for cosine beta, and so on. Because the entire expression sine alpha is replaced by 4/5. And then entire expression cosine beta is replaced with whatever that was, 24, negative 24 or 25. So you replace them as blocks. Each one of those is blocks. Good. So those are the formulas. Let's recap real quick before we draw up another 20 formulas here. These are called trigonometric identities, ways to relate trig functions one to another, and they relate quite nicely. They work quite nicely one with another. As you can see, we have these basic 5 division formulas where you have tangent and cotangent and secant. So that's technically like definitions of those. And then you go into Pythagorean identities. We said the boss equation is this one, accompanied with the proof of why is it so. But then if you shovel the terms, you get these two. Divide by sine squared and cosine squared to get other 6. Now, whatever I boxed in red will be heavily used in calculus later on. So those formulas you really should know. I mean, you will know them because you'll use them so much. And then sum and difference formulas. We have 6, but they are in groups of, 2, so three groups of 2. Sine of plus and minus, cosine of plus and minus, and tangent of plus and minus. Tangent is very rarely used, and it's very rare to find someone who actually knows them because they're just not used so much. But these ones, you're going to remember them just because. And if you're taking a PreCalc 2 class, you will know these formulas just because they are mentioned so many times. But now, for calculus survival and to be able to operate in that environment, we have to talk about double angle formulas and power reducing. And also there are half angle, which are pretty much never seen, but they're there as well, and they are just a simple algebraic manipulation. So double angle formulas. Double angle is a sine of 2 alpha or sine 2x, whatever, sine 2x. Sine 2x or cosine 2x or tangent 2x. Oh, by the way, you notice that I never talked about sum and difference of secant, cosecant, and don't use it. You can derive them, but Now double angle goes the same way. You have sine 2x, cosine 2x, tangent 2x, and if you need any of the other ones, it's just 1 over sine 2x, 1 over cosine 2x. So it's easy to get the other ones. Now, double angle formula. My question is, how much is sine 2x? Right? Now, the way to derive that is to just use the common sense. Well, sine 2x is sine x plus x. And that is going to be sine x cosine x plus cosine x sine x. But then these two are like terms. So it's very quick to see that this is 2 sine x cosine x. So if you use just a basic addition formula where the two angles are x plus x instead of x plus y or alpha plus beta, whatever, we use sine of x plus x, and when you apply the formula from before, you actually get the formula for the double angle. Now this is used a lot. This formula is everywhere. Now much more important, which gives us the other important formula, is the cosine of 2x. And then you can write again cosine of x plus x and work it out. You get cosine squared x minus sine squared x. Now this formula is insanely important. And the reason why it's important is because it has other two flavors. If you replace cosine squared using Pythagorean identity, cosine squared is, remember, 1 minus sine squared, you get 1 minus 2 sine squared x. So cosine 2x can be written in this way. And you can also swap the sine squared and get another flavor of this formula, which says 2 cosine squared x minus 1. So you get these using cosine squared x is 1 minus sine squared x, and sine squared x is equal to 1 minus cosine squared x. Remember, I defined this as a other flavor, Pythagorean identities. So if you use those within these formulas, you get these other two forms. And it's these other two forms that give us the power reducing and the half angle formulas, which we actually need for the power reducing for calculus. At the end of calculus 1, I tell my students, if you don't know power reducing formulas and if you don't want to review and learn those, just don't sign up for Calc 2. That dramatic. So we can manipulate now these formulas to come up with the power reducing formulas. So let's do that. I don't even know how to. You know what? I'm going to put them on a green cloud. There we go. So now, if I manipulate these, take cosine 2x is equal to 1 minus 2 sine squared x, and then move 2 sine squared x to the left and move cosine 2x to the right, and then divide by 2. Wait, this is supposed to say cosine 2x. We get this. You want to take calculus too? Eventually, it's your formula right here. It's called the power reducing formula. Power reducing formula. So if you, when you run into integral of sine squared x dx, the only way to solve it is to write this in the next step and then go on and do the calculus after that. So if you have to integrate sine squared, there's no other way of solving that problem. Forget about it, right? So if you don't know power reducing formula, you just can't do it. So I will need this now because it's a PreCalc review, but you have to know this formula. And then also, if you write the other formula down, which was cosine 2x is equal to 2 cosine squared x minus 1, you can solve for cosine 2x, so, sorry, 2 cosine squared x is equal to cosine 2x plus 1, right? You move 1 to the left and then you swap the sides. You get that the cosine squared x is, and now just swap the order of these over 2. And you get the other power reducing formula if you run into cosine squared, the integral. So generally when students fail Calc 2, it's technically one of the prerequisites and it's mainly trig stuff. You have to know power reducing formulas for sine and cosine in order to do very basic stuff. Again, this, the name of the course is pre-calculus, right? So everything from those pre-calculus courses needs to be known in order for calculus to go well. So these are our power reducing formulas, and there are also half angle formulas, but they show up very, very rarely. I'm not even expecting them to see them on your placement test or whatever. Half angle formulas, again, you exploit the fact that the left side and the right side, so this is a single x and it is 2 times x. So if you just solve for, just take a square root of both sides and do substitution, you are done. Now these formulas again are very rare, but they exist. So let's take a look at half angle formulas. So these are again listed, and they might show up but again, they're not that crazy important. So sine squared x is equal to 1 minus cosine 2x over 2. So this is that insanely important power reducing formula that you have to use. So now what I'm going to do is I'm going to square root both sides, and when I square root both sides I have to put a plus minus on the right. So now I have that the sine x is equal to plus minus square root of 1 minus cosine 2x over 2. And now we use substitution. 2x equals, let's say, theta or whatever. So if 2x is equal to theta, then x is equal to theta over 2. Plug in. And what you get is the formula that sine theta over 2, because x is theta over 2, is equal to plus minus square root of 1 minus cosine theta over 2. This is the same like power reducing formula, except you move the square root to the other side, and you have sine of half angle is a cosine of theta. So you can calculate the sine of 22.5 degrees with this, if you... Again, this is not a formula that generally people memorize because it's so easy to derive from power reducing. You absolutely must know power reducing formulas. Don't bother with anything if you don't know power reducing, trig identities, stuff like that, right? The angle, double angles, and sum. Those formulas you absolutely must know. Now, half angle, because you just square root both sides on a power reducing formula, and you have it. So to use this, you just say compute, let's say sine of 15 degrees. Now you know that 15 degrees is 30 degrees divided by 2. So theta equals 30. Plug in. So sine 15 degrees is equal to sine 30 degrees over 2, from where you use plus minus square root 1 minus cosine 30 degrees divided by 2. You have your plus minus square root of 1 minus, and the cosine of 30 is root 3 over 2 divided by 2. Now, I'll just point here and say 15 degrees is in Q1, quadrant 1. And if it's in quadrant 1, that means that the sign is positive, so we keep the plus only. So keep plus and throw away minus. And what you get is just square root of 1/2 minus square root of 3 over 4. Right, when you take root 3. And that's actually the exact value for sine 15. Now we calculated sine 15 earlier to be, I believe, the square root of 6 minus square root of 2 over 4. Yeah, go ahead and figure out how to manipulate this into that. Fine. Right? That's algebra. It shows those two are equivalent. But this is just the other way to figure out sine 15. Now, as I said, 22.5 is okay because that's half of 45. You can calculate sine of 30 degrees, which you know is half, by working out sine of 60 degrees divided by 2 and use a cosine of 60 there, right? Which would work out because cosine of 60 is a half, 1 minus half is a half, half of half is a quarter, and the square root of a quarter is a half, and sine of 30 is half. So it works. That's the beautiful thing in math. It all clicks all the time. There's not going to be an exception that, oh, this little small thing didn't work. It always works. Everything always works out. And those are the half angle. So, yeah. We just went over 30 formulas in a shot, maybe more. They're all in chapter 5, spread across first 3 sections. Section number 4 introduces another 8 formulas. 4 of those sum to product, and then another 4 product to sum. And we give those formulas to students on the exams. Those formulas do not show up in Calc 1, 2, 3, but they do show up in briefly in differential equations, which obviously hinders the performance there. Anytime you are given formulas, you are severely disadvantaged. There we go. Now, disadvantage for the future because you don't know those formulas, you don't learn them, and then when they show up, I mean, if you were given every formula from Algebra 1, and let's say you're taking somehow Calculus 3 exam and you're dragging with you, a stack of formulas. So, yeah, these things, I mean, if you are not making sense out of any of this material and you are just, mechanically memorizing formulas and practicing problems, clearly you have to fall off the truck very quickly in mathematics because we are barely scratching the surface with Calculus 3 and differential equations and so on. About 20 years of active math studying before you get to the place where the people are right now, and it's just limiting yourself to the one track, one discipline. So you get to pick whether you want theoretical mathematics, applied mathematics, and then statistics and probability, and then within that you get to specify the field and so on. It's no. So everything up to and including differential equations is called elementary mathematics. That's where it ends. And then linear algebra is the first non-elementary math course, and the only non-elementary math course you teach are these. The rest you have to go out of the school to learn. So what I'm going to do is I'm going to say, so I'm just going to write here because it's not relevant to this review and the test you will be taking. So there are 8 sum to product and product to sum formulas out there. You can look at those, and this is 5.4, right? Part. So what I'm going to do now is work out 1 or 2 exercises really quick for identities, and then we are going to hit the break. When we come back, it's time for trigonometric equations. So I'm going to pull from verifying trig identities, which is probable to be present. Something like, this looks bad enough. Verify cosine x divided by 1 minus sine x plus 1 minus sine x divided by cosine x to be equal to 2 secant x. And I put a question mark above the equal sign because we don't know. if this is true or not. That's why I say verify. I make sure that, as I said, you can write anything down. Now, whether it's going to be true or not depends on our calculations. So let's start by analyzing what we can do. So you look at this and you immediately say, well, I have two fractions. And the way to deal with two fractions with a plus in between is to just add them using common denominator. So what is the common denominator? Common denominator is clearly 1 minus sine x times cosine x. Right? And for the top, you get to say cosine squared x when you cross multiply, plus, and now you have 1 minus sine x squared. You have two of those. So it's now just algebra. Okay, let's work more. So that should be equal to 2 secant x. So cosine squared x plus 1 minus 2 sine x plus sine squared x when you FOIL. Don't forget the middle term. Generally, this is the one that kills your grade. When you square a plus b squared, you have a squared plus 2ab squared plus b squared. So it's that middle term there. And on the bottom, I have 1 minus sine x times cosine x. This still needs to be equal to 2 secant x. I have no clue. I mean, it doesn't look good. It doesn't look hopeful, but let's see. I mean, we don't know, right? Something might happen. So now, when I look at this, right, I see that I can just remove these parentheses. I can just remove the parentheses because I don't need them. And wow, I am recognizing this plus that is equal to 1 in the Pythagorean identity. So I have the purple one plus 1 minus 2 sine x over 1 minus sine x times cosine x to hopefully is equal to 2 secant x. Now 1 plus 1 is 2 minus 2 sine x, and this is where I'm happy. Because I see I can factor out 2 in the numerator. When I factor out 2, I'm left with 1 minus sine x, and guess what cancels? Whee! So what you are left with is 2 over cosine x is equal to 2 secant x, but then we know that 1 over cosine is secant, so 2 secant x is equal to 2 secant x. Verified. So that identity that really didn't look good actually works just fine. And just for a practice, I'll give you one to solve. And we'll take a look at it together, and then we'll go for a break. So how about here? They say sine x over tangent x plus cosine x over cotangent x is equal to sine x plus cosine x. Okay, let's take a look at this together and then hit the brake. You can write tangent as sine over cosine and then deal with the double fraction. So we are going to work on the left-hand side and try to make it simplified right into right-hand side. So we have sine x, and this is the main division line, and then tangent is sine x over cosine x, plus cosine x over cotangent is cosine x over sine x. Now that needs to be sine x plus cosine x, hopefully. Now, we deal with double fractions. If you have a over b over c over d as ad over bc. So two that are close by, you go in denominator, and two that are far apart, a and d, they go into numerator. So now you have actually sine x over 1. So using this, I'll just say we have sine x over 1 divided by sine x over cosine x. So what we get from the first one is the top minus, top times all the way on the bottom, so it's sine x times cosine x divided by 1 times sine x, plus, and now for the second one we have cosine x times sine x divided by 1 times cosine x. And that needs to be sine x plus cosine x. Now these guys cancel, and what you're left with is cosine x plus sine x, which is the same as sine x plus cosine x, right, using the commutative rule. So again, it's verified. Okay, so that's the identities. We are going to use some of these identities to solve trigonometric equations, which is going to be the second part. So we'll restart the stream. See you in about 5 to 10 minutes. We'll go for 5.